Well, the possible outcomes of a statistical decision and how we determine the probability of each. We might commit a type 1 error. If we commit a type 1 error, the p-value is the probability of committing that type 1 error when we reject the null. If we reject the null, we might commit a type 3 error, being right that there's an effect there, but wrong about what the effect is. That's estimable, but it's a huge pain in the butt. It's a nasty formula. And in order to apply the formula, you have to know so much about the relationship you're looking at that you probably wouldn't be studying it anymore. So it's not worth calculating in any interesting sense. You might also commit a type 2 error. And if you commit a type 2 error, you want to estimate the probability. If you retain the null, you could be committing a type 2 error, and you'd like to know the probability that retained null is a type 2 error. And to do that, you're going to first find the power in the study, and 1 minus the power is the probability of that type 2 error. Now, here's the complicated part. In order to determine the real probability of each, we have two different approaches. One is the significance test. That's what we were just talking about. The p-value tells us about the probability that a rejected null is a type 1 error. 1 minus the power tells us the probability that a retained null is a type 2 error. What we really want to do is have information from more than one study. We want to use replication and convergent research as our estimate of what's really going on in the population, so we can look across the studies and decide which one's got it right, which one's got it wrong. The only reason we have all these p-values and significance tests and all the rest of this crap is because we're impatient. By design. We want to make a decision based on every sample, and we want to be able to know how likely we are to be right and wrong when we make that decision. Back in the old days, before the 60s and Sputnik and the push and the production of what got turned into what is known as the publish or perish milieu, people would run 5 or 6 studies, go to conferences, talk to each other, make trips, hang out with each other, show each other data. And when they had 5 or 6 convergent studies, they'd pick the one that they thought was most representative and publish that and mention, and we've done this 5 or 6 other times, let me know if you want to see those data. Nowadays, life is a little more up pace. Research demands are certainly a little more up pace. And we literally have to do something useful with each commitment of resources. That is, every study's got to give us something. And so if we're going to look at the results from a single study and draw a conclusion and push that conclusion into the literature, we need to know the probability that we're right and the probability that we're wrong. But what we'd really like to do is run large amounts of convergent research, hang out, and decide what we think we've seen. Okay? And that's why there's 2 layers. There's the p-value and the power, which gives us the type 2 error about this study. But then we still do literature reviews. Nobody gets to do a dissertation without a literature review. Nobody gets grant money without a literature review. Show me that you know what's going on, how it's being done, what we think we found, and if there are any problems. Now, tell me how you're going to run your one study that's going to add something to it. So there's always 2 slices of everything. What we get out of this study and how it relates to the rest of the literature. What is meant by statistical power, and what is the advantage if our research has lots of it? Describe how power analyses are conducted and how they can inform our statistical decisions. Statistical power is the ability to reject the null when the null is wrong. Even though we know the null is always wrong. Still. Rejecting the null when there really is a relationship in the population. It's also known as sensitivity. The ability to detect an effect when an effect is present. The advantage, if our research has lots of it, is we avoid type 2 errors. That's what power analysis is all about. Not missing the wolf when the wolf is there. describe how power analyses are conducted and how they can inform our statistical decisions. There's two different kinds of power analyses. There's a priori power analyses and post-hoc power analyses. A priori power analyses, as their name suggests, is conducted before a study is run. The purpose of an a priori power analysis is to start with an effect size estimate, and I want you to put it this way. I want to know what goes in and what comes out of the two different kinds of power analysis. For an a priori power analysis, we start with an effect size estimate and the amount of power that we want. And we take the effect size estimate and the amount of power that we want and solve for how many participants we need. A post-hoc power analysis, which, as the name suggests, happens after the study is run, and usually only conducted after the study is run and you have retained the null. Now you're doing a post-hoc power analysis to determine the power of the study to figure out the probability that you just committed a type 2 error when you retained that null. To do a post-hoc power analysis, you start with the effect size of the study and the sample size of the study. And you go to the power table to find out how much power that study had. And 1 minus the power is the probability of a type 2 error. How can these inform our statistical decisions? Power analyses only inform retaining the null. Post-hoc power analyses inform us about the probability that we commit a type 2 error when we retain the null. And so when you retain that null and you see that you have a power of 0.2, which means you got an 80% chance that this is a type 2 error, you got to make a decision. You got to think about how comfortable you are retaining that null.
Thank you so much. Thank you, Professor Carl Garvin. You are the best professor, really. I'm so happy to have the chance to be one of your students. I wish you keep teaching and informing the youth. Anyways, I wish also you come to Africa, you go to Ethiopia, and you meet the young scientists and teach them there. But thanks to the internet, I also got the privilege to record your audio and share it with those in my network. And thank you so much for giving me the permission to do this. And thanks to the minds who created the internet technology. Dear friends, now we are going to start from the beginning. Intentionally, I went to the last part of the discussion where, I'm studying questions for this stat class. So I'm going to start from number 1. Enjoy listening. Keep sharing. Sharing is caring. Thank you.
Question 1, what are the 4 major types of behaviors or measures involved in statistical analysis? What procedures can influence which of these we have in a given data collection? How can the data analyst know which type or types are involved in a particular study? Well, the 2 big kinds that we worry about are quantitative and qualitative. Quantitative variables, different values mean different amounts of the underlying construct. Qualitative variables, different values mean different kinds of the underlying construct. We have to be careful because in databases, both of them tend to be represented with numbers. 1 and 2 may mean 1 of something versus 2 of something, or 1 and 2 might be men and women. The other 2 variable types that we want to pay attention to are binary and ordered category. Binary is a qualitative variable with 2 categories. The reason I've drawn binary closer to quantitative is that there is very little disagreement that you can treat a binary variable as a quantitative variable in most of the statistics that we have looked at. For example, the mean of a binary variable makes sense. So does its standard deviation. The mean of a binary variable, the decimal part tells us the proportion of the sample in the higher coded group. That's meaningful. We can use that. If you tell me you coded men 1 and female 2 and you've got a mean of 0.75, 3/4 of your sample was female. It's a meaningful value. We can also stick binary variables in as quantitative variables in any of the statistical models, which means, yes, you can actually run a correlation if you have 2 binary variables. But on the test, if I give you 2 binary variables, I want you to tell me a chi-square. I want you to stick to the basic process. But there is some flexibility. Ordered categories are when you have multiple qualitative variables and they line up. They order. Classic examples are the grading system. A, B, C, D, F. Ordered categories. Different values mean different kinds of performance, but they line up roughly. There is more of a ongoing argument about whether ordered category variables can be treated as quantitative or if they need to be treated as qualitative. We'll do more of that as we go. What procedures can influence which of these are in a given data collection? The choice of the researcher, the data collector, or the data coder. When we're talking about how a variable is operationalized, that's typically the researcher's choice. How does the data analyst know which types are involved in a particular study? Hopefully, it's expressed in the data set. The rule that we've used is quantitative variables don't get value labels. Qualitative variables do get value labels. But the idea is that you've got to know what kind of variable you have in your data set, often by just plain old asking the people who built that data set, built the questionnaire, or whatever. Number 2, what do we mean when we say that our data analyses are inferential, and how do we know whether our inferences are correct? This is one of many questions that deal with what I've consistently referred to as the 2-part goal of our science: representation and inference. Our hope is that our experiments, our studies, our research represents the external validity factors that we're trying to understand. Population, setting, task stimulus, any societal temporal. We hope that we get good representation because we are going to infer as if we do have good representation. Specifically, what inference means is we are not going to settle with a description of our sample. We are going to describe our sample with the intent of inferring that what we have found in the sample describes a broader population. That what we have found in our setting of our study applies to that setting broadly. That what we have found with our task and our stimulus applies more broadly beyond those specific tasks and stimuli. That we've learned something about somebody doing something somewhere more than just our sample. Now, how do we know whether our inferences are correct? The word know isn't the point. We're never going to know. Nobody's ever going to whisper in our ears what's true. So part of answering this question is recognizing that we're never going to know. What we're going to do is try to build evidence. And we're going to try to build evidence that the results of a particular study are worthwhile in 3 basic ways. 1, using good methodology. That is, knowing the methodological part of our research literature and doing those methodological things that have proven useful before. If other people say you've got to run a stratified sample to do a good job, you better go get yourself a stratified sample. If they say we've had a very difficult time running this study well in the field, but we've got great success in a structured environment, you better do that. If people say we've had really good luck measuring this as a binary variable, but when we've tried to measure it as a quantitative variable, we've introduced so much measurement error we get crap, you better run a binary variable. So all that methodological stuff needs to be based on your intense, impressive knowledge of the literature and how the research has been done before. Second of all, replication. Any one study, no matter how beautifully run, might not be beautifully run, and there's always chance. No matter how beautifully you select your sample, no matter how perfectly you randomize, at least at those two situations or operations, chance is also operating, and you may get crap for no fault of your own. So replication is very important. And the third is programmatic research. Extension studies, convergence studies, whatever language you want to use, make sure that I understand this means different people running different versions of the study, looking for patterns of consistency and inconsistency. Number 3, what are the population and sample characteristics that increase and decrease the accuracy of our inferences about the population mean? How should we use this information when designing our data collections? Well, when we look at the population characteristics, population characteristics are very simple. The more complicated, the more complex a population is, the harder it is to represent. So we can call it complexity. Let's, for the heck of it, call it heterogeneity. Heterogeneity increases the difficulty. Homogeneity decreases the difficulty. If you've got a group that's all the same, it's much easier to grab a sample of them that's representative than if you've got a wide, interesting, diverse population. So, what are those things that talk about the sample? Well, there's two things. One is stratification. The more heterogeneous your sample, the more important stratified sampling becomes. If you've got different kinds of people, you need to figure out how to make sure you've got those different kinds of people in your sample. And the other thing is sample size. Larger samples are more likely to be accurate. Once again, it's just chance operating. I had a sampling prof who used to love to say, chance needs a chance. Randomization only gives you the most likely result if you give it long enough to settle in. How do we use this information when designing our data collections? First of all, again, going back to that literature, we need to know enough about our population so that we have an idea of how homogeneous or heterogeneous it is. An answer to an awful lot of questions from here on in are going to be going back to the literature. Not in terms of its content or its findings, but in terms of the methodology that brought us that literature. Second of all, going to the trouble and the expense of getting those stratified sampling frames, and going to the trouble and the expense of getting large data sets. You can only do good stratification if you know what the strata are. And that comes from the literature. Number 4, what does an SEM describe how this can be estimated from a single sample and why this estimation process is reasonable? The standard error of the mean is an estimate of how likely, not how likely, it's an estimate of by how much a population mean estimated from a sample mean is wrong. It's an estimation of how much a population mean estimated by a sampling mean is wrong. In other words, it's the average, or it's the mean error of estimation of the population mean by the sample mean. Standard error of the mean. It's the average error of estimation of the population mean by the sampling mean. In other words, when we draw a sample and we use that sample to infer what is the population mean, how much are we wrong? We're wrong on average by the value of the SEM. Now, the formula for an SEM is the reason for this question, because it just looks funky. The standard error of the mean is the standard deviation over the square root of n. Now, we've talked about how larger sample sizes are more likely to be accurate. So it makes great sense that something that estimates how inaccurate we are has an n in the denominator. The bigger the n, the bigger the denominator, the smaller the fraction, the more accurate was the estimate. That part makes sense. This is the squirrely part, because this is the sample standard deviation. Yes?
Is that a big N representing the intended population, or a
That's the big N, meaning the whole sample.
Oh, it's sample.
Big N is the whole sample. Little n is one group of that sample. But we don't really have a symbol for the value of the population. We sort of assume it's infinity. Remember that the sample standard deviation is inferential, and it's supposed to represent the population standard deviation. And if we put the population standard deviation in that numerator, that would sort of make sense too. Because the more variability there is in the population, the harder that a sample will get exactly the mean of the population. Does that make sense? I mean, if we have a population that only has the values 1, 2, and 3, we're not going to miss by much. It's going to be tough to grab a sample and miss by very much. Does that make sense? The narrower the population standard deviation, the more accurate a sample is likely to be. However, if we have a population that has values from 0 to 100, it's real easy to grab a sample that misses the mean. So the standard error of the mean formula makes sense. How much variability there is in the population? The more variability there is in the population, the harder it is for the sample mean to be correct. That makes sense. And the larger the sample size, the easier it is for the sample mean to be correct. The squirrely part is that this standard deviation isn't the known population standard deviation. It's the estimated or inferred population standard deviation from the sample standard deviation. And that's the weird part, is we're using the sample to estimate the accuracy of the sample.
This can be kind of a yes or no question. Kind of outside. Do we use this to avoid regression to the mean type of errors?
No. No. Regression to the mean is a process of repeated measurement. This is just one measurement from each person. Now, you will get more regression to the mean in a population that has more variation, but not because of this.
Okay.
All right, number 5 is a really important question. We haven't talked about it a lot because I wanted to get a bunch of things in front of you before we talked about it. But it's a real high probability essay question for the exam because it's so very important. Most of the things that we study that are really important are important because they're complicated. It's a complicated statistical model or a complicated methodology that allows us to look at complicated behavior. This is just a simple little univariate question. But it's incredibly important because you've heard of lies, damn lies in statistics. Well, this is in the damn lies category. Damn lies is when the way you collect your data creates the answer that you're going to get. Okay? And that's what can happen here. I can go out and grab a sample, argue what a wonderful sampling technique it was, and still cheat like a son of a bitch. And that's what we're worried about here, is cheating based on sampling. There's 2 different ways of getting a stratified sample. Let's say that our population is 70% one group, 15% another group, 10% another group, and 5% a fourth. Okay? Just to have something fairly complicated to work with. There are 2 different kinds of stratification. One kind of stratification is population strata matching. And as you might imagine, it's got a zillion different terms. But the idea is that the sample has the same proportions of the strata as the population. So for this sample, 70% comes from that group, 15% from that, 10 from that, and 5 from that. Okay, and these are all percents. I'm going to go ahead and put them in. Now, if you've only got enough data, you've only got enough money for your sample to be an N of 50, that means you're going to have about 35 folks here, and you're going to have to make a decision what to do with that extra one. So let's say you make this one 8, and this one 5, and this one down to 2. It means you're representing a strata of your population, a subgroup important enough to identify, with 2 people. Can you see the problem with representing the mean and the standard deviation of that strata with 2 folks? Okay? So we get to the second, which is sample sufficient sampling. And again, that's just one group's words for it. Sample sufficient sampling. Sample sufficient sampling says we want to have enough people in each group that we trust the data about that group from that strata. And so if we had only an N of 50, we do something like we'd want to get as close to equal numbers in each strata as we can.
Is that called sample sufficient?
What? Yeah, sample sufficient is the phrase that's used by sampling theorists that I happen to like. But the idea is that we get, it's also known as proportionally flat sampling, which isn't really a better term. But the idea is we want to make sure that we've got enough people in each subsample to represent that subgroup. Because an average based on 12 people is a lot more palatable than an average based on 2 people. Here's where it gets interesting. There's 2 different things that we're likely to do with our sample. One is to represent the overall mean, which I'll use 2 bars to represent the grand mean. The mean of everybody in the study, which is everybody in the population, we hope. And we also are interested in getting the mean of each strata or subgroup. Because very often, the reason that we carefully sample multiple subgroups is we're going to compare the average on something. Make sense? So there's two different reasons to do stratification. One is to represent the population by getting good strata representation. And the other is to represent each of the subgroups, making sure that you've got good representation of each of them. The problem is, these two things don't go together. Imagine for a second that on some dependent variable, there are interesting mean differences on the DV. Okay? Don't even care what the DV is. But one group tends to have big scores, scores tend to get smaller. If we take this approach, where the proportion in each strata matches the proportion in each strata of the population, our grand mean is likely to be a good representation of the population grand mean. Does that make sense? But we're likely to be uncomfortable comparing those strata to each other because some of those strata have very small samples. That's the trade-off. We've got good representation of the population stratification, but some of those strata are being represented with numbers too small to be comfortable with. If we take the sample sufficient approach, we've got a comfortable number for each group. But take a look at a moment to think what's going to happen to the grand mean of the groups, the grand mean of the sample's ability to represent the grand mean of the population. Do you see the problem? This average, instead of being represented by 70% of the group, like the population, is represented by 25%. This, instead of being represented by 5%, is now represented by 25%. Each of the subgroups has a better chance of being represented with sample sufficient sampling. But the grand mean is likely to be misrepresentative of the population grand mean. Make sense? Okay, so here's the way this gets used. You've got two different groups, both of which are trying to argue that they're the preferred group in the population. Politics is by far the simplest. So you've got Republicans and Democrats, and both of which are trying to argue that the grand mean is aligned with their position. Okay? And, of course, the score, the average score on whatever you're measuring of Republicans and Democrats isn't the same. You with me so far? So if you want to argue that the grand mean aligns with the Republican mean, all you have to do is oversample Republicans. You with me? And then the grand mean will be closer to the mean of the oversampled group. And if you want to prove that the grand mean is more aligned with the Democrats, all that you do is oversample that group, and it will pull the grand mean of the sample in that direction. Make sense? You got to watch for this. This happens all the time. And I'm not just talking about politics. On our own fair campus, the librarians wanted to be tenured. Okay? Because librarians have been without a share of the tenure system for a long time. And one of the things that they wanted to do, that one's harder. Let's do a simpler one. Let's talk about see, all the real examples get complicated.
Who's the librarians? I want to hear about them.
No. Tell you what, I have a handout. I'm going to bring the handout with me on Wednesday, and we'll do this. And I think there's a librarian example in there. All right, so this is the basic answer to 5, and I'll come in with an entertaining version of an example of this, and how all people had to do was change the way they represented whom and got completely different answers. Okay, and that's what I want you worrying about with stratification. Yes?
Do they try and just gloss over that part and
Yeah.
write up?
Yeah.
Like, here's our mean.
Here's our grand mean. We took a representative sample. Now, it's an APA blurb, or it's an AP blurb in the newspaper. They're not going to tell you their sampling strategy. They're not going to tell you the proportions. They're not going to tell you, well, here's the sample, here's the population strata, here's the sample strata, here's the final number. They just say, we know what we're doing, no really. And we're fair and honest, no really. And we got this. See, we were right.
Couldn't you just weight the different means from the sample sufficiency?
The way that you can have your cake and eat it too is to use this sampling strategy, but then use a weighted grand mean, where you take this times 70% plus this times, yes, you can do that. Then all you have to do is tweak what is your claims about the population strata. You can still have your way. Okay? There is no substitution for replication and convergence. That's why we gave up on the critical experiment, whether it's astronomy, chemistry, or demographic sampling. The notion of trust comes tough in this business because it is so easy to cheat. And so what we do is we implicitly and explicitly trust each other and then run out and replicate their results. It's a weird social environment. But yeah, that's the way to fix it. But that fix requires that these numbers be honest and true. So we've changed where the lying, cheating, and stealing occurs. Describe the process of null hypothesis significance testing and tell the possible outcomes. Be sure to tell what the acronym means. It's null hypothesis significance testing. We're going to ask how probable a particular event is. That event that we're going to ask how probable it is the null hypothesis. The process is quite simple. What you do is you get a sample that represents the target population. You collect data. Those data are used to generate a summary statistic. The summary statistic plus the degrees of freedom are used to generate the p-value. We make a null hypothesis significance test decision based on that p-value. Following the well-known rules, if p is less than 0.05, we reject the null and decide there is a relationship between the variables in the population. If p is greater than 0.05, we don't reject the null. Some would say we retain it. And we decide that there is not a relationship between the variables in the population. The important part that I want to make sure you get into this answer is that when we're all done, we act on this decision. That decision is going to either change or not change theory. If we get results that support the theory is in place and may be stronger. If we get results contrary to the theory, it combats that theory. No research result is without effect. And it might change or not change practice. We're not just making mathematical procedures with a conclusion. We are making decisions about what we think describes the world, and that is going to impact our theory and our practice. And this will lead then to replication and to programmatic research. All of that is part of null hypothesis significance testing as it's practiced in scientific empirical psychology and the nice folks who have joined us. It's not just getting a p-value. It's getting that p-value and making a decision. That decision is acted on, replicated, and converged. All of that is the process of significance testing. The possible outcomes are 5. We could have a type 1 error, a false alarm. We think we found something that isn't there. We could have a type 2 error. And don't just list type 1, type 2. Make sure that you specify what each one is. A type 2 error, a miss. There is an effect in the relation, or there is an effect in the population, and we failed to find it in our study. A type 3 error. There is an effect in the population. We found an effect in our sample, but they're not the same effect. In the case of correlations and ANOVAs, we got it backwards. In the case of a chi-square, we got it backwards or sideways. There is also a correct retention. There's not an effect big enough to care about in the population, and we decided we didn't find an effect. We're right. There's really nothing there, and that's what we found. Really nothing. And there is correct rejection. There is something, we found it. We found the right something as well. So part of this is making sure that you have in your head and can articulate the different decision errors. The other part is remembering that what we treat null hypothesis significance testing as something that begins with the sampling and ends with convergent research that accumulates evidence and convinces us that we know what's going on. In other words, significance testing is not a single study phenomena. It is part of the programmatic research. Each study generates a decision. Those decisions accumulate with the others until we get comfortable with what we think is, quote, really going on, unquote. Number 7, discriminate among the various types of statistical decision errors and tell the likely reasons for each. How can we be certain whether or not we have committed one of these errors with a particular analysis? Well, type 1 is a false alarm. We think we found something when there's nothing there to find. It's the classic story of the researcher crying wolf. False alarms happen for several reasons. One of which is bad samples. Samples that don't represent the population can lead to results that don't represent the population. Second, bad measures. If we're not measuring the construct that we think we're measuring, our data don't represent the behavior that we hope it will represent. Also, confounds. If we introduce a confound that's operating in the same direction as our IV, we may get the result we wanted, but not because of the IV, because of the confound. And we must never forget sampling variability. Also known as chance. That carefully, randomly chosen sample from a complete population sampling frame might, by chance alone, not be representative. That carefully completed randomization procedure to assign people to conditions might, by chance alone, not work. Type 3. A misspecification. There's something there. We found something, not the same something. This is the boy who cried wolf while he was about to be eaten by a bear. Yep, there was something there to be afraid of. Wrong something. All of the same things that produce false alarms produce misspecifications. Bad samples, bad measures, confounds, and chance. And the third is type 2 errors, known as a miss. This is when a boy is quietly sitting on the hill watching the sheep and the wolf is eating his parents. There was something there. He missed it. Now, the sources of that are the same as the sources of type 1 and type 3 errors. Bad samples, bad measures, confound, sampling variabilities, plus too small samples, which means a lack of statistical power. Without a doubt, the most annoying of all. When you get exactly the result everybody else has gotten, but yours isn't significant because you couldn't afford the last 20 people. Okay? Describe the univariate significance tests applied to quantitative and qualitative data, including the null, the usual research hypotheses, and the two different ways these tests are often applied. If we have one qualitative variable, we talk about the chi-square goodness of fit test. The goodness of fit test has a null hypothesis about the specific response distribution. In other words, if we've got people who love dogs, people who love cats, and people who love reptiles, the null hypothesis is about a specific distribution. It doesn't have to be that they're all the same, but the null is some specific population that we think describes what's going on in the population. The null hypothesis is about the population distribution. The research hypothesis, most of the time, is the null, because we're describing the group we hope to have sampled. And so the research hypothesis, again, most of the time is the null. We want to find a particular pattern. If we have one quantitative variable, then we're talking about a one-sample t-test. The null hypothesis is that the sample will have a specific population mean. And again, the research hypothesis, most of the time, matches the null. Not always, but most of the time. The null is that the sample matches some specific hypothesized population mean. Mu is just X bar for a population. It's a parameter instead of a statistic. The two different ways these tests are often applied. One, to check if our sample statistics match known population parameters. To ask if our sample statistics match known population parameters. In other words, asking if our data match our target population. The second way these tests are often applied is to test hypotheses and learn new things about the target population. If we're sure our sample matches the target population, then we start asking questions about the population from the sample. And most of the time, these two get used together. First, we use some of these tests to ask if our sample matches the target population on known parameters. And when it does, then we try and learn new things from this sample. Now, if we try and do the second without the first, we could really stick our foot in our mouths. Until we're sure that our sample represents the target population, we might not claim to have learned new things about the target population from that sample. And so they're often used in conjunction. This is one of those, if I could change the world, one of the deals. If I could change the world, we would do a lot more careful checking that our sample matches known population parameters before we start adding to the parameters we claim to know from that sample. But I think, after playing this game for a while, that we don't check the quality of our sampling any more than we check the quality of our random assignment for exactly the same fear. That it didn't go well and we don't really want to know. That $450,000 worth, just to name a current number, $450,000 worth of sampling later, it didn't work quite as well as we wanted to. Let's just go ahead and trust chance. But those are the things that we can do with it. Question 9 starts by asking what are the 3 bivariate significance tests we will use and how we decide among them. We've got 2 kinds of variables that we're going to identify to drive our choice of statistical analyses. Variables are either quantitative or qualitative. And the very first way of thinking about when to use what statistic is that if we have 2 quantitative variables, we're going to use a Pearson's correlation. If we have 2 qualitative variables, we're going to use Pearson's chi-square. And if we have 1 of each, we're going to use F or ANOVA. Number 10, state the generic null for each of the 3 types of significance tests. Tell what parts of the are common to the null of all 3 tests, and what part of each is specific to that particular test. Well, the most generic is that there's no relationship between the variables in the population. Relationship between variables is the most generic expression of the null hypothesis. As we go into each of the statistical models, we see a slightly different representation of no relationship that's used to help the reader, to get the reader and the analyst on the same page, so that the statement of the null presages the analyses that are coming and things like that. With the correlation, we talk about no linear relationship. With the chi-square, we talk about no pattern of relationship. And for the ANOVA, we talk about no difference between the means. Now, we know that these are just expressions. No difference between the means. The one above it? No pattern of relationship. That's an arrow. Okay. What's what? No relationship between the variables in the population. Now we know that this is just an expression, no linear, no pattern, no difference, because we know that we can turn chi-squares and f's into r's. We have effect size estimates. So we know that this is just an expression that's designed to aid communication. You can always talk about whether or not there's a relationship between the variables. The different statistics use different kinds of variables, and so different, slightly more precise representations of how to think about that relationship. But it all comes down to this generic null, that there's no relationship between the variables. Number 11, what are the possible research hypotheses and outcomes of an ANOVA analysis? Okay. Well, research hypotheses come in three kinds. Group 1 does poorer than Group 2. Group 1 is equivalent to Group 2. And Group 1 does better than Group 2. This is where researchers and practitioners somewhat diverge from statisticians. We accept the notion that there might be a difference between the groups that's not big enough to care about, to act on, to change theory, or to change practice. And again, we've got 5 possible outcomes, 2 of which are correct. A correct retention, and a correct rejection, 3 of which are errors, type 1, type 2, and type 3. And when you answer this question, I want you to tell me what those are. All right? I'm not going to tell you what those are right now because we've said them 3 times today. But even if you have to write them 3 times on the test because of the particular set of questions you get, write each question as if it's the only opportunity you have to convince me you know what's going on. Okay? All right, number 12. When can the results of an ANOVA be used to test each of the major types of research hypotheses? Well, research hypotheses come in 3 major kinds: attributive, associative, and causal. The question is, when can an ANOVA be used to test each of these? Attributive? Never. An attributive hypothesis is a univariate hypothesis. It's about the existence of a behavior, its ability to be measured and discriminated from others. It is a univariate question. No bivariate analysis can be used to support it. Associative research hypotheses can always be tested by ANOVA. Anytime you've got one qualitative variable and one quantitative variable, you can whoop it into an ANOVA, and you can ask if those 2 variables are associated or statistically related. Because remember, an associative research hypothesis only needs one type of support: a reliable statistical relationship. Causal research hypotheses can only be tested by ANOVA when the design is a properly conducted true experiment without confounds. In other words, when can an ANOVA be used to test a causal hypothesis has nothing to do with the fact you're using an ANOVA. Any set of statistical outcomes can only be causally interpreted when the design is a properly conducted true experiment without confounds. No? Thought you were warming up. And number 13, compare and contrast the uses of between groups and within groups ANOVA models. The design is different for between groups and within groups models. Now, I know the language overlaps, but let's make sure we understand how and why that language overlaps. A between group ANOVA is applied to a between groups design because that between groups ANOVA is set up to compare the means of two groups represented by different people. So a between groups ANOVA uses a between groups research design. A within groups ANOVA is used when you want to compare the means of two groups that are represented by the same people. And later in the course, we'll show you how the ANOVA model for between and within is different and explain this a little more. But the statistics are set up with different assumptions about where the data come from. That's why you will sometimes see a between groups ANOVA referred to as an independent groups ANOVA. It assumes those two sets of data are independent of each other. And a within groups or repeated measures ANOVA will sometimes be referred to as a dependent groups ANOVA, because it assumes that there are relationships between one of the scores in this group and one of the scores in that group. And the reason the scores are related is they come from the same person. And that's what's known as a lack of independence in statistics. The null hypotheses, all the data, the data are still one qualitative variable and one quantitative variable. That qualitative variable is known as the IV, or groups, or conditions, or treatments. The quantitative variable is known as the DV, or the outcome, or the response variable. The null hypothesis is the same for both, that the groups have the same mean. And statistically, they have the same range of values from 0 to infinity, and a p-value means exactly the same thing for both. Now this next set of, 14, what are the possible research hypotheses and outcomes for a Pearson's correlation analysis? Be sure to cover all the possible decision errors. There are 3 possible research hypotheses: positive linear relationship, negative linear relationship, no linear relationship. Make sure you get the word linear in there. Make sure you express all 3. One of the differences between statisticians and researchers and practitioners is sometimes we think we're not going to get enough of a relationship to care about. And we refer to that as hypothesizing the null. There are 3 possible results of a statistical analysis using Pearson's correlation. We either decide there's a positive relationship, decide there's no relationship, or decide there's a negative relationship. This sets up 9 possible outcomes, each of which is a combination of what's true and what we decided. And we end up with 5 things among those 9 possibilities. 1, a correct rejection. We think we found something. What we found is what's really true in the population. A correct retention of the null. We didn't find anything, and we're right. There's nothing going on in the population. A type 1 error, a false alarm. We found an effect. There's not an effect in the population. A type 2 error, a miss. We didn't find anything, we should have. There is something in the population. And finally, a type 3 error. We found something, there is something, but not the something we found. A misspecification. When can the results of a Pearson's correlation analysis be used to test each of the major types of research hypotheses? You should notice that these two questions appear for each of the three families of statistics: ANOVA, correlation, and chi-square. Okay? As far as we're concerned, the statistics are interchangeable and driven by the variables that we're working with. But the process is the same. And what I want you to do is to capture the process. That's what's most important. There are three major types of research hypotheses: attributive, associative, and causal. A correlation can never be used to test an attributive hypothesis because an attributive hypothesis is a univariate hypothesis. Correlation is a bivariate statistic. It asks about the linear relationship between two variables. Attributive hypotheses are about measurement, not about statistical relationship. A correlation can always be used to test an associative hypothesis, no matter what sort of design you have. An associative hypothesis is supported by a reliable statistical relationship. Doesn't matter what kind of design you have. Anytime you want to know if two variables are related and they're quantitative, whoop out that Pearson's correlation and test that associative hypothesis. A correlation can be used to test a causal research hypothesis anytime you've got a true experiment highlighted by random assignment to conditions and manipulation of the independent variable and no identifiable confounds. So you got to remember, there's the two things that define a true experiment: random assignment of individuals, manipulation of the IV. Then there's the second question of whether or not there are any confounds. There's two issues there. One is randomization doesn't always work. Second of all, you have the whole procedural ongoing equivalence thing to take care of. It is entirely possible to have a quantitative variable to which you have randomly assigned and manipulated participants, analyze the data with a correlation, and give it a causal interpretation. We tend not to. Most of the time we manipulate categorical variables and we measure quantitative variables, but there's nothing that prevents having an independent variable that has multiple different quantities, each of which is manipulated and randomly assigned. (16) What are the possible research hypotheses and outcomes of a Pearson's chi-square analysis? When you have a 2 by 2 chi-square, let alone anything bigger, there are a whole bunch of different possibilities. There are 8 different patterns available in a 2 by 2 chi-square. So in order to simplify things and keep them manageable, we're going to talk about a research hypothesis about a particular pattern, a research hypothesis that there is no pattern, and a research hypothesis about a different pattern. All we really need to capture this is a focused pattern, a null pattern, and some other pattern. The outcomes are, we either get the pattern we were looking for, we get a null pattern, or we get a different pattern than we were looking for. Now in the population, either the pattern we're looking for is true, no pattern is true, or there's some other pattern. Make sense? That's all we need to capture the 9 outcomes and grab them up in the 5 categories, which are still correct rejection of the null. The pattern we found is the pattern that's in the population. Correct retention of the null. We didn't find a relationship, and there isn't a pattern in the data. Type 1 error. We found a relationship, there's not one in the population. Type 2 error. We didn't find a relationship, there is one in the population. And a type 3 error. We found a pattern, there is a pattern in the population, but not the pattern that we found. So it's the same basic thing. 17, when can results of a Pearson's chi-square analysis be used to test each of the major types of research hypotheses? Again, Pearson's chi-square is a bivariate statistic, so it can never be used to test an attributive hypothesis, which is a univariate hypothesis. You don't ask if something exists, can be measured, and can be distinguished by other things by correlating it, by chi-squaring it, or by ANOVAing it with other things. You can always use a Pearson's chi-square to test an associative hypothesis when you have two qualitative variables. Doesn't matter what kind of design. And, as with the other statistics, you can use a Pearson's chi-square to test a causal research hypothesis whenever you have a true experiment with no identifiable confounds. And there's more and more of that in psychology, as psychologies are sort of reevaluating and rediscovering categorical outcome variables, diagnostic outcome variables, conditions, kinds, varieties. Instead of amounts, we're seeing a lot more chi-square analyses than we did 10 and 15 years ago. So you still got to make sure, whether it's an ANOVA, a correlation, or a chi-square, that you look at the design to decide what kind of interpretation to give the data, associative or causal. All right, 18 is a high probability question. Because if you can't identify what statistic to use, none of the rest of your statistical knowledge is going to do you any good. And this is the most complete characterization that I know of how these four statistical analyses relate to each other. So compare and contrast the interesting pair of the four bivariate data analysis models we're working with. One, test for bivariate association. If you have two quantitative variables, you use a correlation. If you have two qualitative variables, you use a chi-square. Just want to know if two things are related, and often that's how we characterize them. The difference is, if we have two quantitative variables, we use Pearson's correlation to look for linear relationship. If we have two qualitative variables, we use Pearson's chi-square to look for a pattern of relationship. Second pair. When we're comparing means. When we've got two conditions, and we have a quantitative dependent variable in each, we're going to use an ANOVA. We have two ANOVAs, between groups ANOVA and within groups ANOVA. Not surprisingly, we also have two kinds of designs, between groups designs and within groups designs. So if we're comparing means, and it's a between groups design, we will use a between groups ANOVA. If we're comparing means and it's a within groups design, we'll use a within groups ANOVA. The third one, going in order of increasing probability of getting it wrong, is when we have a between groups design and we have a quantitative outcome variable versus a qualitative outcome variable. The choices here are between groups F and a Pearson's chi-square. The Pearson's chi-square will be used when we have a between groups design, that is, two groups on the IV, and a categorical or qualitative outcome variable. Now we've got two qualitative variables, but we're thinking about it as comparing means. It's comparing groups. If we want to compare those groups on a quantitative outcome variable, we then use a between groups ANOVA. The one that causes the most heartache, the one that is your greatest opportunity to shine by getting it right, is when to use a correlation and when to use a within groups ANOVA. Both of them can be applied when you have two comparable quantitative variables. Pre-post. Two measures of the same variable in a within groups design. If you want to know if those two quantitative variables have a linear relationship, you use Pearson's correlation. If you want to know if those two quantitative variables have different means, then you use the within groups ANOVA. The important part of making this decision is first deciding correctly whether or not the variables are comparable. So if I have your height when you're 10 and your height when you're 15, I can reasonably ask, does your height at age 10 predict your height at age 15? I can also reasonably ask, are you taller at 15 than at 10? Make sense? I mean, age or height at one age, height at another age are comparable. It makes sense to compare the means. If, however, I have your height at age 10 and your weight at age 15, it still makes sense to ask if one can predict the other, if there's a linear relationship between your height at 10 and your weight at 15. But it makes no sense to compare the means. How are we doing? So you got to stop and look for comparability. And those are the interesting pairs. And if you can think that way, you have two ways to get to each of the four statistics. And that will dramatically increase your chances of correctly selecting what statistic to use when. Tell the components of a complete null hypothesis and how its expression differs with each of the following. The complete expression of the null hypothesis involves the idea that there is no bivariate relationship between the variables in the population represented by the sample. Remember that null hypotheses, like research hypotheses, are about what's going on in the population, not what's going on in your sample. Your sample is there to represent the population. The language that we use to express no bivariate relationship changes across the models. If it's a Pearson's correlation, we talk about no linear relationship in the population. If it's a Pearson's chi-square, we talk about no pattern of relationship in the population. If it's a between groups or within Groups Anova, we talk about no mean difference between the between the populations represented by the groups. So again, that simple language, no linear relationship, no pattern of relationship, no mean difference. Always referring to what's going on in the population. There's one page in the details of bivariate tests that has all of this all gathered together. Tell the symbolic null, the range of possibilities, the basis for null rejection, and how one describes the direction or pattern for each of the following. The symbolic null for the correlation is R equals 0. No correlation. The range of possible values for a correlation is from negative 1.0 to positive 1.0. The basis for null rejection is p less than 0.05. And make sure that you capture the direction of the linear relationship in your description of the result. Chi-square. The symbolic null is chi-square equals 0. The range of possible values is from 0 to positive infinity. The basis for rejecting the null is p less than 0.05. And the description is about the pattern of relationship. And remember, chi-squares take more words to describe than all the rest of them, because you got to describe a whole pattern. Between groups and within Groups Anova both have the same symbolic null, that the means are equal. And once in a while, you'll see, most of the time you'll see this. Once in a while, you'll see this. And you should recognize that they're the same thing. If they're the same, their difference is 0. The difference is 0 is an older notation. It's sort of morphed into the other one in the 60s and 70s, came back for a while in the early 90s. Now we've settled back into same as each other, instead of not different from 0. The people who like the not different from 0 recognize that that's how the math works. You don't really ask if they're 0, you ask if they're different. You don't ask if they're the same, you ask if they're different. Which is just a little too anal for me. The range of possible values for the F is from 0 to positive infinity. The basis for null rejection is p less than 0.05. And you want to make sure that you describe the direction of the mean difference. So there's direction of linear relationship, pattern of relationship, and direction of mean difference. Yes?
Where did you say that was all grouped together?
The between and within ANOVA are the same thing.
No, I mean, you said it was, is it in one of the PowerPoint slides, or is it on one of those?
No, it's on a PowerPoint slide. There's actually two of them together that I refer to as a comfort page.
Okay.
And they're sort of blocky, gritty looking things. Let's just take a second. There. There's your expression and all of the, most of that information, and then this is just a reminder about that language. We talk about non-significant and significant. We don't talk about meaningful and insignificant. Sure. '21 is also a high probability question because it's amazing how often this gets screwed up, misrepresented, taught badly. Respond to and describe the statement rejecting the null hypothesis guarantees support for the research hypothesis. No, doesn't. The null hypothesis and the research hypothesis have to be considered separately. You should first use the p-value to decide whether or not you're going to reject or retain the null hypothesis, and then you have to evaluate the research hypothesis. The easiest way to talk about why this statement is false is to point out the two counterexamples. One is when the research hypothesis is the null. When the research hypothesis is the null, rejecting the null is contrary to support for the research hypothesis. The other possibility that happens way more often than we wish it did is when you reject the null hypothesis, but the data pattern is different from what you hypothesized. Okay, so you got to separate the null hypothesis from the research hypothesis. What are the three positions in the null hypothesis significance test controversy? Which do you prefer and why? This is a real which do you prefer and why. Okay? I want an opinion. The three positions are ban the null hypothesis test. Don't use it in any form, in any guise, in any way, ever. Never make the decision whether or not there's a relationship in the population. The other extreme is everything's just fine. The way we've done it forever, although not consistent for more than 4 or 5 years at a time, is just fine. The middle ground has been that we're pretty much stuck with null hypothesis significance testing because it is a firmly entrenched tradition, and so we should do the best possible job of it, emphasizing power analyses and the use of effect sizes. Sliding in a confidence interval whenever you can. Now, that position has won, both by edict and by public acclaim. That doesn't mean that's the one you should like. Okay? A little idealism now and then is good for all of us. And so I'm interested in what you think. I mean, people who like the ban it can very convincingly say, the nil null is goofy. There's never no relationship at all. There's never no pattern at all. There's never no mean difference at all. It's silly. And so it's a silly place to start our analysis. The people who like it say, hasn't really hurt us badly so far. And frankly, it's not the sloppiest thing that we do. The people in the middle, it's always easier to be in the middle. To say part of it's good, part of it's bad, here's how to do it better. So I want you to stop and think and decide how you feel about this. And for that reason, this question happens a little more often than the others, because I want to get a window into your thinking. 23, what are confidence intervals and what three types did we explore? What does a confidence interval tell you that is redundant with a null hypothesis significance test? What additional information is provided by confidence intervals? Confidence intervals tell us the range within which we are how confident the population parameter exists. The range within which we are how confident the population parameter exists. And we looked at three population parameters that we might care about. One, a single population mean. So the confidence interval around a single mean tells us the range within which we're how confident the real population mean lands. A 95% confidence interval means we're 95% confident that the real population mean is in there somewhere. The second is a mean difference between two populations. The parameter, what's the real population mean difference? And so we have a confidence interval around a mean difference. So we take the mean of one sample, we take the mean of the other sample, and we calculate the sample mean difference. That's our best guess of the population mean difference, but we want a confidence interval around it. And the third is the one that's most important, because it's the confidence interval around a correlation. And there's two reasons why that's important. One, we do more correlations than we do ANOVAs. And second of all, much of the time when we do an ANOVA, we translate it into a correlation to have an effect size. So a confidence interval around an R can also be used as a confidence interval around an effect size for any study. How strong is that effect? And within what range do we think the real population strength lies? A confidence interval can always be used to replicate a null hypothesis significance test. The easiest example is that a 95% confidence interval duplicates the information from a p less than 0.05 significance test. If the null value is within the confidence interval, retain the null. Whether that's a null about a particular mean, a null about a mean difference for which the null value is 0, or the null about a correlation for which R equals 0. If the null value is in the confidence interval, retain the null. If the null value is outside the confidence interval, reject the null. So you can always get a significance test from a confidence interval. What information or what additional information is provided by the confidence interval? The width of that confidence interval gives us an idea of the amount of power and believability our sample has. Huge confidence intervals mean we're not very confident. Small confidence intervals mean we have greater confidence. Either the population is easier to predict or we've got a big old honking sample. Either way, narrow confidence intervals increase our comfortableness with our conclusions. And second of all, the null hypothesis test is always about one end of the confidence interval or the other. And the confidence interval gives us both. That confidence interval is a wake-up call. I have a correlation of 0.3. That's my best guess of the correlation in the population. My 95% confidence interval goes from 0.1 to 0.45. I'm going to interpret the 0.1, the 0.3, and the 0.45 all very differently. And that's what I mean when I say that confidence interval gives us both ends, and therefore is a useful wake-up call. How excited would you be about these results if you had the smallest value, if you had the largest value? It also reminds us how important power is to make those confidence intervals as narrow as possible, and how important replication and convergence are, because even confidence intervals, which are better than point estimates, is still just one sampling, one study. And we gave up the idea of the critical experiment way long ago. And so those confidence intervals let us know just how much risk we're taking when we say we know what's going on. It is a very important wake-up call. Describe effect size estimates. Tell how they're related to significance test, the information they provide that is not provided by significance test. Effect size estimates try to tell us how large the effect is without being influenced by the sample size. In other words, if there really is a population correlation of 0.3, and you run a good small study, and I run a good large study, we should both get that 0.3. Okay? Effect sizes are explicitly designed to not be influenced by sample size. How they're related to significance tests? One way to get an effect size is to take a significance test and strip the sample size out of it. That's why most of our effect size estimates are an F over the degrees of freedom, or a chi-square over the sample size. Very simple math that is literally taking the significance test, which is a correlation of effect size and sample size, stripping sample size out, leaving effect size. It's amazing how simple that algebra is and how long it took us to figure it out. What information they provide that is not provided by significance tests? Significance tests and effect sizes are trying to do two different things. Effect sizes are an estimate of the size of the effect. Significance tests are estimates of the probability that the effect exists. And yes, they're kind of contradictory. One says, how big is it? The other one says, is it probably there? And the reason they're contradictory in a sense is that effect sizes don't take sample size into account, significance tests do. So you can have an effect size that seems substantial, but based on a sample size so small that you just aren't comfortable trusting that it's different from zero. And that's why you put the two together, especially if you take the effort to look at that p-value to estimate the probability of a type 1 error and crank out the power to estimate the probability of a type 2 error. Suddenly, they begin to flow together, and you have a nice system for evaluating your results.
Yeah, thanks so much. Thank you, Professor. And this is really very nice. I hope our students, especially masters and PhD students in Ethiopia, in Africa, in other developing countries, even in Western countries, can benefit from this. Researchers also, there is a possibility that we can learn from this, thanks to the minds that gave us the internet technology, and thanks to people who have the knowledge and the expertise, and those who are willing to share what they have with the bigger world. And I thank Professor very much. And let's study together. And it's okay if we understand it or not, but for sure there are a lot of points that we get out of it. Yeah, I'm learning a lot, and I'm really glad that I met Professor before he is retiring. And these words will live forever, and a lot of young people are going to learn from it. እንግዲህ ወጣቶች በያላችሁበት ይህንን አድምጡ፣ ለሌሎች ደግሞ አካፍሉ። ማካፈል መተዛዘን ነው። Sharing is caring. This is our philosophy, and I wish you very nice time wherever you are. Thank you so much. This is Fakadu Ratta from Youth and Education Support Service Ethiopia. Yes, Ethiopia. Currently a PhD student at the University of Nebraska, Lincoln. Leadership, Education and Communication Department. Thank you so much.